In this lecture, we will continue our discussion on reactive intermediates, and in specifically the one that we're looking at is that of radicals. As a quick review, last lecture we looked at the detection and characterization of radicals. You may recall that since radicals have an unpaired electron based on that spin, and in the presence of a magnet, it can be detected. Experiments such as electron spin spectroscopy and susceptibility experiments, we can detect radicals. Next, we looked at the structure and bonding of radicals. So we concluded that the methyl radical is definitely sp2, and most carbon radicals are sp2, but based on what's bonded to that carbon, it could look more like an sp3 with that odd electron in an sp3 orbital. Next, we looked at the relative stabilities. And there are two primary factors that contribute to the stability of radicals, and those are hyperconjugation, or sigma bonds adjacent to the radicals, using those electrons to stabilize the radicals, hyperconjugation, or resonance, which is really the delocalization of that odd electron across atoms. We looked briefly at the generation of radicals, which are basically the homolytic cleavage. Remember, it's the homolytic cleavage because a single bond has two electrons, and if it's broken homolytically, one electron will go to one fragment and the other electron will go to the other fragment, hence radicals. And we briefly looked at some reactions of radicals. But we will continue our discussion today on the reactions of radicals. So in this lecture, we'll review a bit more on the generation of radicals, and we'll concentrate on the reactions of radicals, the rearrangement reaction of radicals, and then we'll look at the mechanisms involved in radicals as an intermediate. So first, this is the generation of radicals. So here we have a chlorine bonded to another chlorine. So here is that sigma bond with two electrons. And if that bond should be broken based on the supply of heat or light, notice that energy must be supplied to break that bond. We indicate that breakage using an arrow, single barb arrow. So one electron goes here and the other electron goes here to form two radicals. Benzoyl peroxide. Peroxides are known for forming radicals in the presence of energy, typically heat. Let's see why. So here's the peroxide here. This is the sigma bond with two electrons. If broken, one electron goes here, as you can see, and the other electron goes here to form a radical. This radical that's formed is resonance stabilized because it can be delocalized from here over to here, as shown using these arrows for resonance. Notice again, this is a symbol that's used to represent resonance structures. Here's another one, azobis butyryl nitrile, AIBN. So here's that compound. Here is nitrogen double bond. So that's a tough bond to break, but here's a single bond to that nitrogen, and here's a single bond to that nitrogen. So it's possible to break this bond here homolytically. So one electron goes here and break this bond homolytically, so one electron goes here to form nitrogen gas. As you may recall, whenever a gas is released from a reaction, that's a very favorable reaction due to entropy. What's left behind, however, is a radical forming at this carbon. So here's a radical. Again, you may recall that the CN group is C triple bond N. So this radical is again stable because it can be delocalized onto the nitrogen. Let's look at propagation of radicals. So in these type reactions, we're not looking at the initiation of radicals. Just to refresh your memory, most radical reactions take place in 3 steps as part of the mechanism. We'll see that in a second. The initiation step, which is the production of radicals, and then the propagation, which is production of more radicals, and of course the termination. So in this propagation step, or in a propagation step as shown here, let's look at the methyl radical. So we have a radical, and we have here tri-N-butyl tin hydride. It is known as a hydrogen atom donor. So remember again, a hydrogen atom is really a hydrogen radical. So you can see here what results is this hydrogen is transferred here, just one electron, hydrogen atom, and what's left behind is a tri-N-butyl tin radical. Propagation. So in other words, we have generated another radical from a radical. Here's another propagation type reaction, and this is used typically in the synthesis of polymers. So we have a radical here, and the functional group here is an alkene. So as you can imagine, what we can have here is that this electron comes here, this electron comes here to form this bond, and the other electron goes onto that carbon. Notice I'm using a single barb arrow to show the movement of one electron, not a double barb. If I use a double barb, that would be showing the movement of 2 electrons. So this electron comes over here, and we have created another radical. That's a propagation step. As I mentioned, these reactions are very useful in polymer synthesis, and just here's an example. So we have what's called a radical initiator, could be a peroxide, whatever. In the presence of energy, this bond is broken homolytically to give radicals, 2 radicals. This radical can add to an alkene to form another radical here, and in the presence of another alkene, it continues. So we can see here that's the polymer chain that's been built up. Of course, radicals are intermediates. So in a termination step, we have here these 2 electrons coming in to form a bond right here, and that is how the reaction chain is terminated. So this becomes the polymer. Let us look at another type reaction of radicals. In this case, we have here a radical, here it is, and on the same molecule we have an alkene. So as you can imagine, this would be an intramolecular reaction compared to the different, as we have seen on the previous slide. So we can form a bond to this carbon or to this carbon, as you can imagine. So here are the possibilities for this propagation step. If it forms right here, you have here a primary radical. If it forms over to here, you form a secondary radical. So you know that the secondary radical is more stable than a primary radical. But it is shown that this is 50 to 1, so we have more of this. The question is, why do we have more of this and less of this if this is more stable than this? The explanation is that it's much easier for this radical here to find that carbon closer in proximity than finding this carbon over here. So the kinetics is very fast. The kinetics is very fast, so that's why we have a lot more of this unstable radical, more of this radical, even though it is not as stable as the other one due to the kinetics involved. Here's another example. Intramolecular radical reaction again. Here's a radical, here's an alkene, but in this case we have a phenyl and a phenyl here. So in this case it will bond here, and of course the other electron here, and put in the other electron on that carbon. You can see here, this is now resonance stabilized based on the phenyl group. You may recall that the phenyl group is really that. So the odd electron can be delocalized into the phenyl ring. This is possible, but it's not as stable. So this is formed in abundance. Why? Because this is closer to the radical and it's more stable due to the phenyl compared to this, which just has hydrogens, which just has one hydrogen actually right here, a secondary radical, which is not as stable as a radical that's on the adjacent carbon of a phenyl ring, also known as the benzylic radical. So look out for that in terms of your mechanisms. Let's look here at rearrangements. So radical rearrangements are possible, but not nearly as frequent as we find in carbocations. You may recall from your undergraduate organic chemistry that once a carbocation is made, it's possible to do rearrangement. It happens here, but not as frequent. So let's look at a few. So let's look at this radical. This is a primary radical here, and here is a phenyl ring that's bonded to the adjacent carbon. Over time, it can migrate over to this carbon, putting the radical here. So that's observed. The question now is, how did that take place? It's a migration. So this phenyl ring here literally migrates over to this carbon through this. So you can see here that the radical is now stabilized by the phenyl ring as it migrates, and we end up with that. So again, you may want to look at this again, make sure you understand the migration of a group from one carbon to the next carbon, which has a radical, and the migratory aptitude depends on how well the group can stabilize that odd electron as it migrates. So the phenyl ring has a great migratory aptitude. Let us now look at reaction mechanisms. You may recall that a mechanism is really a step-by-step description of a reaction. As you know, a reaction, well, most reactions don't typically occur in one step. They occur by creating different intermediates, and the intermediates react and keep reacting until we have a final product. So let's look at this example, which we have seen before, and that is the chlorination of methane. So you have chlorine and methane in the presence of light. What will happen? So as we said, chlorine in the presence of light or heat energy, this bond will break homolytically to give two chlorine radicals. That's called the initiation step in the mechanism. Chlorine radical is very reactive. It sees two electrons here it takes one of these electrons from this carbon hydrogen single bond to form HCl, leaving behind a methyl radical. Notice that's a propagation step. Why? Because a radical generates another radical. In another step, we have here the radical, the methyl radical, as you know, is very reactive. It sees another mole of chlorine, which has 2 electrons right here. It takes one to form this bond here with this electron and leaves behind a chlorine radical. That's another propagation step because a radical generates another radical over here. The final step involves the methyl radical reacting with another chlorine radical to form a neutral product, chloromethane, and that's called a termination step. That's called a termination step. So these are the steps in the reaction mechanism for the free radical chlorination of methane. Let's look here at other products. As you can imagine, for the same reaction we looked at before, once we have generated the chlorine radical and we have made chloromethane as our product, it's still possible to have a reaction. So chlorine radical will react with one electron of this sigma bond to form HCl, leaving behind a radical. So that's the chloromethyl radical. As you can imagine, the chloromethyl radical is reactive because it's an intermediate. So it sees another mole of chlorine. It can take one electron from here with this one electron to form a bond. And now this is a neutral molecule here. Dichloromethane generates another chlorine radical. And of course, this step would be a propagation step if you were to label this step. So this is an unexpected product based on what desired, but it's a possible product. Here's another possible product. We could take the methyl radical, which was generated from the previous slide, and another methyl radical, 2 electrons, can form a sigma bond right here, and a neutral molecule, and that's ethane. So as you can imagine, for the halogenation or the chlorination of a hydrocarbon or an alkane, there are many possible products based on the intermediate, the radical intermediate that's generated. So in industry, what's done is to control the desired product by the concentration of either the halogen, the chlorine, or the hydrocarbon. So based on the concentration of both, they can determine which would be the major product here. Let us look at another concept. If we had propane and we subjected it to chlorination, we get 2 possible products because we have hydrogens here and hydrogens here. We have 3 here because that's a primary, and we have 2 here because that's a secondary. Notice there are 2 possible products because it can take off this hydrogen or one of these hydrogens here. If it took off this hydrogen here, one of these hydrogens, we have this product. And one of these hydrogens here, we have this product. Notice the concentration of the products though. It's about almost equal. Just slightly more of the 2-chloropropane. On the other hand, if you use bromine, same starting material, the distribution of halogenated product is a lot different. Here, this is 98% by taking off this hydrogen, or the substitution of that hydrogen, compared to the hydrogens here on the methyl carbon. Just 2% of this. Whoops, spelling, Y-I-E-L-D. And 98% here of the product here in the secondary position. Let's see if we can figure out why. As you know, here's propane. It has two different types of bonds. It has here a secondary hydrogen and a primary hydrogen here. Of course, as you know, this bond is weaker because the radical that's generated is more stable. This bond is stronger because the radical that's generated, the primary radical, is less stable. So that is why we have a mixture here, because the chlorine radical that's generated in the initiation step is not very selective. It will react with this hydrogen or one of these. So it's almost 50-50. On the other hand, however, bromine, which is generated in the initiation step of the reaction, it is not as reactive as the chlorine, so it's more selective for the weaker bond. So here's a secondary CH bond. Right? Notice this is secondary because we have the carbon here and over here. So it's still propane, but just drawn a little differently here. So this is the secondary hydrogen, and it's more selective for this to get this radical, more stable radical. But this will also happen, reluctantly happen, to generate the primary radical, because it's not as reactive, very strong bond, so that will form in a very minor quantity. So as you can imagine, the product here will be the termination step, where these two electrons here on the radical and on the bromine forms this bond here as the major product, as the secondary radical. But since we still have some of the primary radical around, it's possible to form a bond right here, and that becomes the minor product, which was, as we have seen, about 2%. So again, the bromination of an alkane is much more selective for the tertiary, secondary, and primary, compared to the chlorination, which is not selective. It will chlorinate just about all hydrogens possible on the molecule. You may be wondering, why not use the other halogens such as fluorine and iodine? Fluorine radicals are just so reactive that it reacts explosively. Iodide radical is just so stable that it does not react, so it cannot break these bonds to form the iodoalkane. So for halogenation of alkanes or hydrocarbons, alkanes, the halogenating agent is typically chlorine or bromine. Okay, let's look at mechanisms in a little more detail. So here's a question. Using arrows to show electron movement, propose a reasonable mechanism for the reaction shown below. So you will see questions like this on your exams, just to make sure you apply your analytical thinking and your knowledge of radicals and their reactivity. So my suggestion, if you have a question like this, where you had to propose a mechanism by using arrows to show how electrons move around from the reactant to form the product, is to carry out an analysis. So the analysis strategy is to observe. The first observation here is that this reagent here generates radical, especially AIBN. Looks like it should generate radical. Typically we have here heat. Sometimes it happens at room temperature, but to be on the safe side, we typically put heat. So this bond breaks to generate radicals. That's one of the first observations. We can make another observation that this CBr bond here is a weak bond and it's possible to break that bond to generate radicals. So it's possible to have a homolytic breakage here to give that radicals. Notice again we have this tributyl tin hydride. As we mentioned earlier, it's a hydrogen atom donor. So it donates typically H dot, H radical or H atom. So with that said, oh yeah, another observation is this is a 5-membered ring right here, and this is a 6-membered ring. So more than likely, there's a ring expansion. So with all of this information, you'll have to put it all together and propose a mechanism for this reaction. Let's see how we can do that. As you can imagine, the first step is the production of radicals from AIBN. So here's the radical. Because gas is given off, but that's the inorganic product, but here is the radical. This radical now sees bromine and can abstract one of these electrons here to form this bond, and the other electron is right here. That's a primary radical. So that's one of the intermediates that's formed. As you can imagine, it's not stable, so it will do whatever to gain stability. Let's see what it will do. It will react to form here a bond and put the electron onto oxygen. So if this radical comes in here, one of these electrons come here and the other one goes onto oxygen, we have here a cyclopropyl and this. Okay, in the next step, as you can imagine, because we need, this is a 5-membered ring and a 3-membered ring, highly strained. So it will do whatever to release that strain, and in particular, if it can do a ring expansion, it will do that. So if this electron comes back in, this goes over to here to form this double bond here, the odd electron goes here. And in this case, we have a 6-membered ring, which is a radical. And of course, we know the function here is for this to give a hydrogen atom to the radical, or hydrogen radical to the radical here, to get the final product, which is shown here. So again, you should be able to look at reactions of this type and explain how it goes from reactant to product by radicals reacting to give different intermediates. Let's look at another one. Same wording, using arrows to indicate electron movement. Propose a reasonable mechanism for the reaction shown below. Same strategy I would suggest. Analyze what's here. And you can see here benzoyl peroxide and heat, definitely radicals. So in my mechanism, I would definitely propose radicals as intermediate. But look at this. This is CCl3 and a Cl. This is CCl4. So it is suggesting that there is a cleavage of a CCl bond to form radicals. Oops, this should be Cl4. Breakage of this bond to form a trichloromethyl radical and a chlorine atom. So we know that's possible. We know that has to form in order to get this as the product. So now all we have to do is to put all of this together and see if we can communicate that using arrows and intermediate to show how this reactant is transformed into that product. So the first step is not surprising. Benzoyl peroxide in the presence of heat gives the radical. Since we know that we will have to break this bond here, let us do it. So we generate this. And the next step, as you can imagine, here is the CCl3 radical reacting here and put the radical over here. Not surprising, what we've seen before. A radical reacting with an alkene, a double bond. What happens next is we need to, of course, as you can imagine, this is highly strained. It's a bicyclic radical. So it's highly strained. So we'll do just as what it did before to release that strain. So if we had a radical here, one electron comes in here, one electron from this bond comes in, and the other one goes over here, we have this. Just that now we're going to pull this over. So we have this radical here. So here's my double bond that was created by this arrow movement, and my radical goes up here, which is right here. And the last step, as you can imagine, chlorine dot reacts with this to form a bond right here. So again, you should be able to propose mechanisms to explain the formation of products from, or typically one organic product from a reactant. Another one, this is a known rearrangement known as the Barton rearrangement. So let's look at this. The question is, can you explain how this reactant goes to form that as a product? How did that occur? Well, I see light here, which means that that energy is used to break bonds, and the weakest bond, and it will break homolytically if the bonds have equal electronegativity. So as you know, the carbon-carbon bond is pretty strong. Carbon-carbon bond is pretty strong, won't break. Same for the carbon-hydrogen bond, pretty strong, won't break in the presence of light. But here we have this over here with some heteroatoms. This bond more than likely won't break. It's a double bond. So in the presence of light, more than likely this bond will break to produce a radical. So that's our observation. So it's possible to produce the NO radical. So it's going to be floating around, and here we have a dot. But then we see that there's a hydrogen from here that goes over to here, and the NO looks as if it's now bonded to this carbon. So it looks as if that's what should happen to give the product. So again, I'm emphasizing the strategy before you propose the mechanism, because you need to see what should happen or what could happen as you propose your mechanism. So let's see, I put here, we looks like we have a 1,5 migration of hydrogen. Looks like this hydrogen migrated over to here, and here it is, Y15, 1, 2, 3, 4, 5. So let's put all of this together to explain the Barton rearrangement. So here we go. In the presence of light, of course, as you will recall, this is another symbol for light, H nu. Breaks this bond, not any other bond, because they are much stronger bond than right here. Breaks this bond homolytically, because one electron goes here and one electron goes onto the nitrogen to form this radical. So we have two radicals. Initiation. This radical here, we know we need a hydrogen. So this hydrogen migrates over here. Of course, it's close enough. I shouldn't say migrate, but it reacts because it's close enough to react. And we have here this OH. But what happens here is, by the way, there should be another arrow right here. This radical now exists, and we have a radical and a radical, and we form here this intermediate. So that's essentially the product, but it's not very stable. There's an equilibrium here, much like the tautomeric equilibrium, where we have the hydrogen here. These electrons come in and these go out, so the hydrogen is transferred over to here and form the more stable nitrogen-carbon double bond. So that's the Barton rearrangement. So once again, you should be able to look at a reaction, the reactant, the reagents that are used, reaction conditions such as light or heat, determine what could possibly happen, and use that information to predict a possible mechanism. Notice I'm saying predict a possible mechanism. We do not know exactly what is the mechanism, but we know what are the rules in chemistry, stability of radicals, etc. And we use that knowledge to explain the formation of different products. Okay, let's look here at another aspect. So you will recall that if you're trying to substitute a halogen for this allylic hydrogen, it's possible to use bromine and heat. So we use heat to break this up into Br dot, and it keeps going to form the allylic radical, and the allylic radical in the termination step reacts with the bromine atom to form the product. However, you will recall from your general organic that bromine can also add to a carbon-carbon double bond in an addition reaction. So you can see you have a problem here if you're trying to get this as your desired product and you use bromine, because we'll also get a trans addition across the carbon-carbon double bond. So how do we get around that? We get around that by using a special reagent called N-bromosuccinimide, also written as NBS. So if you use NBS and heat, it will selectively take off this allylic hydrogen and substitute a bromine. Same for the benzylic hydrogen to produce a bromo product. Let's see why that works. So let's look at the mechanism. Notice we're always getting back to the mechanism to explain different observations for reactions. So we have N-bromosuccinimide in heat or light, typically heat. This bond here is it will break. It's the weakest bond here. So it breaks to give a radical in an initiation step. So here's a radical. So this radical now will abstract this hydrogen to produce the allylic radical, an HBr. In a second step, in another step, this HBr that was generated reacts with more of the NBS here to form this. It's an acid-base reaction, as you can imagine, acid and base. So we have this. It continues to react here. The bromide reacts with this here until we get succinimide and bromine. Notice we do get some bromine here, but it's in very low concentration because it depends on the initial concentration of NBS. So it doesn't have, we do not have enough here to react with the carbon-carbon double bond. In another step, as you can imagine, we have created the allylic radical. So we have some bromine here. We get the brominated product and more bromine radical. So you can see the step, it continues. So this would be one of the propagation steps that generates the product, but there are termination steps in this reaction. Bottom line is, if you have this compound here, cyclohexene, Notice this is your allylic carbon, which has hydrogens here, or allylic hydrogens. If you want to selectively convert that hydrogen, or one of those, to bromine, it's best to use NBS, N-bromosuccinimide, in heat or light to get this as your product, instead of using bromine and light. Finally, let's just show you one of the practical aspects of the radical chemistry that we have studied. As you know, we are environmentally conscious. So here is a refrigerant, Freon. As you can see here, it's a chlorofluorocarbon, CFC, and it's used in our air conditioning units and in our refrigerators, etc. And based on the mechanics of pressurizing it and releasing the pressure, it gets very cold, and that's what is used to cool the environment. But some of it will escape into the environment, and of course, as you know, if it escapes into the environment, there's UV light in the environment, and it will break one of these bonds to produce two radicals. A chlorine radical, if it's in the environment, especially high in the atmosphere, it will react with ozone, here's ozone, to produce that and oxygen. You may say that's good because we're producing oxygen, but as you can see, we are depleting the ozone concentration by that reaction. So that is why it has been recommended that we no longer use these type of CFCs, chlorofluorocarbons, as refrigerants, because it is destructive to the environment, particularly to the ozone layer. So that's one of the practical aspects of the radical chemistry that we're studying here. I think this is the end of that lecture, and it is. So my encouragement to you is to continue reading, and in your textbooks and on the internet or other textbooks, if you can find any information on radicals and the reactions of radicals and the mechanisms that are involved in terms of radicals, just read up on that. And I will post another lecture shortly, perhaps next week, but I will send an email so you have more information on how to prepare for the upcoming exam. Okay? Bye.